Happy Friday to everyone. Today is class for Friday, the 27th of March, and today's objective is to understand the terms used in trigonometry. But before we do that, let's look at an example where we can apply what we've learned so far. I occasionally see cadets out playing wall ball. Suppose this is the wall, and somebody standing back here throws the ball at a 30-degree angle to the wall, and it hits 15 feet up the wall. The question is, how far did the ball travel? Well, we can assume that the wall is 90 degrees to the ground. So this is a right triangle. This is a right triangle. I see it's a 30, 60, 90 triangle. If this is the short side, I know the hypotenuse is twice the short side, or 30 feet. So I can conclude that this cadet must have thrown the ball 30 feet. I could also figure out how far away from the wall he's standing, because I know the long leg is 15 times the square root of 3, which is about 26 feet. So I can use trigonometry to say I'm 26 feet from the wall, and I threw the ball 30 feet. But suppose I don't throw it at a 30-degree angle. Suppose I throw it at a 15-degree angle, and it only goes 7 feet up the wall. Now, how far did the ball travel? I don't know how to do this problem because this is not one of my special triangles. It's not a 30, 60, 90 or a 45, 45, 90. Those are the only two triangles we know how to solve right now. Today, we're going to start looking at how to solve all right triangles. In today's class, we're going to define a lot of terms today, so you might want to stop this video, fill out your notes with all the new terminology before you continue, because you'll probably want to refer back to this as we work through next week's class, applying all these new terms. First one we want to look at is trigonometry. What does the word trigonometry mean? Well, the first part, trigonon, is Greek for triangle. So trigonometry is going to relate to triangles, and metron, the Greek word, you probably heard it mostly as metric, means measure. So what we're going to be doing in chapter 8 is measuring triangles, which we're used to doing, and we're going to do it both by measuring angles and sides. So here I have a right triangle. Have I defined the shape of this right triangle if all I know is this is a 90-degree angle? And the answer to that is no, because this side here could look like this, it could look like this. Okay? If all I know is one angle, I have not uniquely defined the shape of this triangle. So if I was to stand here, I stood here, and I measured this angle to be 20 degrees. Okay. I don't have to come over here and measure this one. I know what this angle is. This angle is going to be 70, because I know the three angles in a triangle add up to 180. So I measure this one to be 20, and as soon as I do that, and I know this is 90, I have now defined the shape of this triangle. Okay. I know that this is a triangle with angles 20, 70, and 90. The new terms that we want to apply for trigonometry, though, is if I measured this angle here and I was standing here, this side of the triangle is known as the opposite side. It is the side opposite of where I measured this 20-degree angle. And this side of the triangle is called the adjacent side. And we don't need to name this side of the triangle because we already know what that is. Here's my 90-degree angle. What is always across from the 90-degree angle in a right triangle? The hypotenuse. So if I uniquely defined the shape of this triangle by measuring a right triangle here and determined it was 20, I now can describe the sides of the triangle as having a hypotenuse, a side opposite of the 20-degree angle, and a side adjacent to the 20-degree angle. What if I had come over here on this one and I stood up here. Now I'm standing up here, and I measure this angle to be 70. Okay? Well, this angle would have to be 20. And even though this triangle is smaller than this triangle, we see that it is similar to this triangle. Okay? So if I'm standing here at the 70, I still can define these sides using these terms. Okay? The hypotenuse never changes. The hypotenuse is always the side across from the 90 degrees. But since I measured this angle to determine that my right triangle was a 20, 70, 90 degree triangle, this side here is now the side across from me or opposite me. This side is now next to me. I can reach out and touch it. It is adjacent to me. Okay? So notice if I was standing over here, this was my opposite side. Now if I'm standing here, this side is now my adjacent side. So the terms adjacent and opposite are always in relation to what angle you're interested in, or I like to think of it as where you're standing. Okay? Now notice I didn't draw a picture standing at the 90 degree angle, because if you think about it, you cannot uniquely define the shape of a triangle by standing here at the 90 degrees, because you don't know these two angles. Okay? All you know is this one's 90. That doesn't define the shape of the triangle. So you can stand here or you can stand here to define your opposite and adjacent sides, but you can never stand at the 90 degree angle. So make sure you have those in your notes, and we'll continue in a minute. Now we're going to take our new terms of opposite side, adjacent side, and an old term, hypotenuse, and apply it to similar triangles. Let's take a 30, 60, 90 degree triangle. If I take all the 30, 60, 90 degree triangles there are, and I line them up and put their 30 degree angle right here, they would look something like this. Okay? If the opposite side from the 30 was 5, I would know that this length right here would be what? Short leg, hypotenuse, it would be double. Similarly, if I had a 30, 60, 90 degree triangle with the short leg of 7, and I lined it up like this, it would mirror this one. It would fall right on top of it because it's the same shape. And now my hypotenuse would be 14. And if I had a yet bigger 30, 60, 90 triangle with this length being 10, now my whole hypotenuse is going to be 20. Right. Let's take a look now at a ratio. Okay. Here's all my opposite sides. Again, think about it as if I'm standing right here. Okay. These are all my opposite sides, and these never change. They're always the hypotenuse. So let's make a ratio of my opposite side over my hypotenuse. Okay. In the first triangle, what would that ratio be? It would be 5 over 10. Okay. So for the first triangle, it's 5 over 10. For the next triangle, if I'm standing here 30 degrees, the opposite over the hypotenuse is 7 over 14. And finally, for the largest triangle, again, standing at the 30, my opposite over hypotenuse is 10 over 20. Well, what I notice is that these are all equal, and that makes sense because I know they're similar triangles. This is equal, they're all equal to 1/2. You should all have that in your notes by now. So what I observe here is that the ratio of the opposite side to the hypotenuse, if I'm standing at the 30 degree angle, is always 1/2. So let's go back to that wall ball example we talked about earlier. If I'm right here at the 30 degrees and I throw that ball 30 degree angle against the wall, if I want to see how far the ball travels, that's X. Okay, what I know is that this is the opposite side and this is my hypotenuse. So I know that the ratio of the opposite side to the hypotenuse has to be 1/2. But in this problem, the ratio of the opposite side to the hypotenuse, the opposite side is 15. The hypotenuse is really what I'm trying to figure out, how far the ball traveled. Well, I know how to solve that. If 15 is to x as 1 is to 2, you can cross multiply, x is 30. And that's what we figured out before in that problem, that the ball traveled 30. But not all problems are going to be this easy. It's not always going to be 30 degrees there. Okay, let's take a look at the other example. Put that up while you finish your notes. For my other wall ball example, I knew I was 7 feet up on the wall, but I only threw it at a 15-degree angle. Now, I know that all right triangles that have 15 degrees here, 65 here, and 90 here are similar. So the opposite over hypotenuse ratio is always going to be the same. I just don't know what it is. We're going to find out next week how to find that. For right now, I'm going to tell you that it is 0.259. Okay, and that is the ratio of the opposite to the hypotenuse for a 15-degree angle if I'm standing right here. This being the opposite, this being the hypotenuse. So this is the opposite, and this is the hypotenuse, which is what I was trying to find. So now I can say that 7 over x is 0.259. How am I going to solve that? Well, if you think about it, this is still a proportion. The 0.259 is just a ratio over 1. So I can still cross multiply, and I get 0.259x is equal to 7. If I divide both sides by 0.259, okay, go ahead and do that on your calculator. These cancel, so I get x is equal to 27.03. That makes sense if you think about it, because before, when I was 15 feet up, I was throwing it 30 feet. Now, if I come down closer, I'm only going to be throwing it 27 feet, which really makes sense because remember, when we figured out before, we were only 26 feet from the wall. So if it's not going that high up the wall, it's not going to go that much further than the 26 feet that you're standing away from the wall. The important thing that I want you to notice, though, is that the ratio of the opposite to the hypotenuse is not going to change for this shape. No matter if I blow this up or I shrink it down, the ratio of the opposite to the hypotenuse will always be this number. Okay, we'll talk more about where this number comes from next week. So I know that this ratio is an opposite to hypotenuse. It has to equal to 0.259. So I can make it a proportion. I can solve for x. And now I have a way to find out how far the ball went, even if it's not one of the special triangles we talked about. Okay, that's really where we want to go in this chapter, is to start solving problems for any right triangle. To help us understand the rest of the terms we're going to introduce today for trigonometry, we use the acronym SOHCAHTOA. This is on your theorem sheet, so you can take advantage of everything it says on your theorem sheet to help you understand how this helps us to find certain ratios in right triangles. The OH stands for opposite over hypotenuse, the ratio that we were just talking about. But to always say opposite side over hypotenuse is lengthy, so we try to use an abbreviation just to make it easier to solve problems. The S in SOHCAHTOA stands for sine. The C stands for cosine. and the T stands for tangent. These words are all representations of ratios. Just rather than say the ratio of opposite over hypotenuse, we just say sine. Sine means a ratio of opposite over hypotenuse. So you could almost think of between the O and the H here, there being a ratio symbol. Being a ratio there, being a ratio there. Because we define sine, we abbreviate it in mathematics as SIN. But what sine means is it's the ratio of the opposite side over the hypotenuse, just like the example we just did. What cosine means is we abbreviate cosine as COS, and it means the ratio of the adjacent side over the hypotenuse. And tangent, we abbreviate as TAN, and it is nothing more than a ratio of the opposite side over the adjacent. And the important thing you have to remember about all of these is it's all relative to where you're standing in the triangle. And that's what comes right after the word sine. So in that last example where we talked about 15 degrees, we would say the sine of 15 degrees is the opposite over the hypotenuse ratio. I'll give you an example of that in a minute with an actual figure. But for right now, what you want to have in your notes is that the acronym SOHCAHTOA stands for sine, cosine, and tangent with the SC and T, and the two letters that directly follow define what sine means. So sine is a ratio of opposite over hypotenuse. Notice opposite goes on top because it's listed first, opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent. So these words right here, sine, cosine, and tangent, are just words that are shortcuts to describing ratios. It's just easier to say sine rather than to say the ratio of the opposite over the hypotenuse. That's a lot to say, and especially when we want to write formulas, it's easier just to say sine and not write this all the time. Okay, so here's what you want to have in your notes. Sine means opposite over hypotenuse. Cosine means adjacent over hypotenuse. And tangent means opposite over adjacent. Okay, so we'll do a couple of examples to help understand how these apply to a triangle. All right, make sure you have what SOHCAHTOA means in your notes. Sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent. Let's see how that applies to a problem. Here I have a triangle. I know this is 30 degrees, this is 90. So this is a 30, 60, 90 degree triangle. So if my short side is 6, I know the hypotenuse is 12, very good. And my long side would be 6 times the square root of 3. So I've already solved this triangle. I know all the angles and I know all the sides. But I want to use a known triangle so we can see how we start defining sine, cosine, and tangent before we start using these to actually solve triangles. All right, let's look at sine of A. The A is very important here. That tells me my reference point, where I like to think of it as where I'm standing. So if I'm standing right here and I measured that 30-degree angle, okay, I know that sine is opposite over hypotenuse. So if I'm at this point A for 30 degrees, my opposite side is 6 and my hypotenuse is 12. So the sine of A is 6 over 12, which is 1 over 2. We will often use decimals to define these ratios. So as a decimal, that would be 0.5. 1/2 is 0.5. You will also see trig ratios written instead of a vertex here, a 30 degrees. These mean the same thing. This means find the opposite over the hypotenuse of the 30-degree angle. So again, both of this term A and this 30 means you're standing here. Sometimes it'll tell you to stand at a vertex. Sometimes it'll tell you to stand at an angle. Either way, you're standing at the same point in the triangle. So if I was to take the sine of 30, I'm still standing here. My opposite over hypotenuse is still the same. It's still 6 over 12. Okay, so this is still 1/2, 0.5. What I want you to realize is this is two ways of asking for the same thing. In other words, it's two ways of telling you to stand here. Okay? Now, if I wanted to take the tangent of A, notice I'm still standing at the same place. I'm still at point A. But tangent is a different ratio. It is the ratio of the opposite side over the adjacent, not the hypotenuse. So if I'm standing at A, my opposite side is 6, and my adjacent side is 6 radical 3. We should all know how to simplify that now. That would simplify to the square root of 3 over 3. Okay? If that's confusing, make sure you hop on Monday with the Zoom meeting, and I'll explain in more detail how we got this number. But I could put this in my calculator, square root of 3 over 3, and if I did that, I would get this decimal, and we normally round to the nearest 100 as 0.58. Okay? So I would say the tangent of A, or the tangent of 30 degrees, is 0.58. So these last two, cosine of C and tangent of 60, would be if I was no longer standing here, I am now at C. So now I'm standing here. So if I wanted to take the cosine, let me move these down. If I wanted to take the cosine of C, okay, what is cosine? Adjacent over hypotenuse. So if I'm here, what side is adjacent to me? 6. What is the hypotenuse? 12. That never changes. The hypotenuse is always the hypotenuse. So now my adjacent over hypotenuse is 6 over 12, which is 1/2, or as a decimal, 0.5. Okay. Notice my cosine from here was the same as the sine from here. That makes sense if you think about it, because if you're standing here and you do the opposite over the hypotenuse, isn't that the same as standing here and doing the adjacent over the hypotenuse? That will always be the case. So these two numbers being the same is not an accident. That will always happen. Finally, if we're up here at C, let's go ahead and take the tangent of 60. We can write it as 60. 60 is another way of saying stand here. Tangent, here's my tangent, is opposite over adjacent. So if I'm standing here, what is my opposite over my adjacent? 6 radical 3 over 6. 6 is canceled. It's just radical 3. If you put radical 3 in your calculator, get 1.73. Okay. Notice my tangent number here went above 1. Sine and cosine will always be between 0 and 1. Tangent can go above the number 1. So make sure you have that in your notes. I'll put one more example up here, and I'll let you work through the trig ratios, and that'll be it for today. All right, last example of the day. Here I have another 30, 60, 90 triangle. If this is 30 degrees and this is 90, I know this is 60. So this is similar to the triangle that we just worked with. Only now this side is shorter. It's only 3. Well, if this is the short leg, my hypotenuse would be double that, 6, and my long leg would just be the square root of 3 times bigger. Okay? So I have solved this triangle. We're going to use this solved triangle now to write these ratios out. So I'm going to pause the camera. You can work through all of these, and then we'll check our answers. And then what I'd like you to do over the weekend is look this over and make sure that it makes sense to you, because next week we're actually going to start using this information to solve problems. Let's work through the first one together, and then I'll let you fill these in. The tangent at D. So Where am I standing? I'm standing right here. I either like to, sometimes I always like to draw the figure or just put your finger here. Somehow you have to realize this is the angle you're at to define the tangent. And the tangent is opposite over adjacent. So if I'm standing here, my opposite over adjacent is 3 over 3 square root of 3. And if you put that in your calculator, you'll get that to be 0.58. And if we were to simplify this, so see these cancel, it's 1 over radical 3. If you multiply that by radical 3 over radical 3, you would get, in a simplified version, radical 3 over 3. Okay. So now what I'd like you to do is go ahead and write in radical form and decimal form all of these ratios. Okay. Make sure you know where you're standing. Either draw your little man in, that's what I do, or put your finger on the place that you're told to. Fill in all these ratios, go ahead and simplify them, and go ahead and write in your decimals as well. We'll check it to see how you're doing. And all right, let's take a look and see how you did. For sine of f, we're standing here. And if we want sine, that is opposite over hypotenuse, or 3 radical 3 over 6. That reduces to radical 3 over 2. In your calculator, you should get 0.87 in decimal form. For cosine of 30, we're standing here. Cosine adjacent over hypotenuse. So if I'm standing here, adjacent over hypotenuse, my radical would be square root of 3 over 2, or 0.87 in calculator. For sine of d, I'm standing here. Sine opposite over hypotenuse. Again, that's 1/2. Notice that's what we got in the other example. We had the sine of 30 degrees was also 1/2. The only difference in that previous example is that it was bigger, but it's still similar, right? And if it's similar, that ratio is going to be the same. So we would expect to get some of the same answers for the same ratios as the previous problem, because I purposely chose a triangle that was similar. I want you to see that those ratios are always going to be the same. That's the secret of how we're going to use these terms to solve problems. Next is the cosine of 60. 60 is up here, so now I'm standing here. Cosine is adjacent over hypotenuse. Again, 3 over 6. Okay. So those numbers are the same. That makes sense because the adjacent over the hypotenuse here is the same as standing here and taking the opposite over the hypotenuse. So it makes sense that these two numbers are the same. Finally, the tangent of f, I'm standing here. And if I take the tangent, it's opposite over adjacent. It's 3 radical 3 divided by 3, which is just radical 3, or 1.73. Notice this number is larger than 1. Sine and cosine, if you think about it, can never be greater than 1, because for sine and cosine, hypotenuse is always in the denominator. The hypotenuse is always the largest side in any triangle. There's no way that this side or this side can be bigger than 6. 6 has to be the longest side. So if I make a ratio of either one of these over the longest, biggest number, 6, I'm always going to get a number less than 1. The only time in a trig ratio where you're going to get a number greater than 1 is for tangent. Here, tangent of f, if you're standing here, tangent is opposite over adjacent. If you're standing here and the opposite side happens to be longer than the adjacent side, you can get a number larger than 1. And so that's a good way to do a common sense check. Sine and cosine, you should always get a number less than 1. Sometimes tangent can be greater than 1 if from where you're standing, the opposite side is the longer leg. All right? So there's a review. Quick review problem on sine, cosine, and tangent. I know this is a lot of new terminology. Can be confusing when you first look at it, especially since sometimes this is a letter, sometimes it's a number. It's just a way of saying where you're standing in the triangle. If I had asked for the sine of E, what would the sine of E be? The sine of E we cannot do. Okay, remember, you can never stand at the 90-degree angle because that doesn't define the shape of the triangle. As soon as you stand here and you know this is 30 degrees and you know it's a right triangle, I know the shape of the triangle. Therefore, my ratios can be set. All right, so that's it for this week. Remember, you should have 1 daily quiz in Blackbaud and 3 homeworks now. Okay. This week, I will accept late homeworks. So if you need to work on some computer issues to be able to get into Dropbox, continue to work those. I need those 3 homeworks. If you can't figure out the Dropbox problem, make sure you just at least email them to me so you get credit. I will accept all 3 of these homeworks late this week only, and the daily quiz you should already have back to me. Otherwise, there is no homework for this weekend. We'll pick up this notion again on Monday. Have a great weekend.